Well, I mean,
Okay. Anyone else have homeworks they want to give me? Yeah. I'll just stamp it when we get back to it. Oh, that's fine. I'll grab it. Thank you. Anyone not get a homework back that they're due? Okay. Okay, some of the common themes I noticed in the homework. Lots of folks started out homework problem 1, how I wanted to see it, with like detailed understanding of that they knew where they were going, they were going to try this, that, and the other thing, and then that disappeared. So second problem, third problem was just algebra. Okay, don't just show me algebra. For me, algebra is inconsistent with understanding. Right, I need to understand that you can approach any problem. For me, doing the algebra is good. You need to do that in order to be able to demonstrate that you did the problem, but it's not sufficient, right? Also, I saw some folks doing a very interesting thing where they were in an XY coordinate system, okay? And they had maybe a dipole like this, okay? And they said, well, now the thing to do, because the dipole turns, is to go into a polar coordinate. Why is this justified? Right, do angles exist in XY coordinate systems? No, in fact, they do. So don't just switch because you see the letter theta, okay? I saw folks introducing a phi. I was like, why? This is not a 3D coordinate system, it's a 2D coordinate system. R and theta are perfectly fine ways to solve the problem. And most people, if they did it carefully with R and theta, they got the right answer. But if you introduce phi, I don't know how you got even close to the right answer. Okay? What you want is x, y, theta. That is perfectly fine. Okay? And so that justification for why did you make these switches? Why did you choose this, that, and the other thing? This is what I want to see in the written homework. If you turned in 1 page of homework, I'm going to guarantee that it's wrong. The reason for this is that you need to be writing out everything you're doing. Okay. Questions before we get started? You'll note that there was only 2 problems in this week's homework. That's fine. I'm not going to stick to 3 problems just because that's what I guaranteed. But as we get into magnetostatics, we'll probably get 3 this week, maybe 2 next week. Okay. Anything else that I'm supposed to talk to you about? Okay. So we were talking about magnetism inside of individual atoms, and then we're going to abstract that to larger concepts. So thinking of an electron as a little loop of current, right? And so then every single loop is going to feel the effects of magnetic forces. Okay. I think I'm going to do this a little bit out of order, mostly because I don't want you to start with a problem. Unless, do you guys want to start with a problem since it's early in the morning?
Yeah, sure.
Who woke up before 9? Who didn't wake up before 9? Me too. Okay, so maybe my brain is like your brain and we should start with a problem just to get it going. Is that reasonable? Okay, so this will be a homework problem, but let's think about it in the context first of maybe just trying to wake our brains up from Thursday. Okay. So the book, we were talking about these little loops, and the book said something along the lines of the force is equal to the gradient of M dotted with B. What was M again? The magnetic dipole moment. So this is telling us that for a specific atom, right, an individual item, that it has this inherent vector that allows it to be perturbed by the dipole. Okay. M dot B, what's the B here? It's magnetic. What's this one? What's that? This one here?
Is that D or is that something else?
The Dorito.
Gradient.
The gradient, good, okay. Okay, so this is the force that acts to move the dipole, right? Oh, hold on, how do I have to change this view? Hi, John.
Hello.
Nope, not that one. How do I hide non-video participants? Nope. There we go. Okay. That'll mess up the recording. All right. So this is the force on the atom that you have an infinitesimal. Let's imagine that you have the positive charge here and you have a negative charge going around it. So this is acting like that loop. And then you put it inside of a B field. Okay. And perhaps this B field is non-uniform. Okay, this would move the loop around. Okay. Let's think about it though in the context of forces. Let's imagine that we have two. Okay. Or that they stole the good markers. I learned that you're not supposed to do that. That's what Martin told me. There's the beefs. Okay, so there's some separation here. Call it R. What is the force of M2 on M1? What? Yeah, so here all I have is I just have two things. Neither of them are moving. And there is no electric potential here. These are simply magnetic dipoles. Do they operate on one another? First question is there an electric field? Let's look at this little object here. Why yes? Okay, but at this location that I put the little dotted line, is there E here?
Is still the magnetic field going through that surface?
No. I'm just asking about electric field. So you have a positive charge and a negative charge. One's orbiting the other. No. Why no?
Because it cancels each other out.
Because the enclosed charge is
Zero.
0. Okay. So to large distances, that's definitely true. As you get closer, there's different quantum mechanical effects. But for the purposes of what we're looking at here, we're going to assume two dipoles, magnetic dipoles, don't have an E interaction between them. So typically we would say something along the lines of the force is something like QE and
V cross B.
Q
Q V.
V cross B. Okay, so this is 0. Why is this 0?
Well, they're not moving.
Well, all right, so this is a little tricky. We'll get back to this in a second. Okay. All right. So you have a moving charge. Where's the moving charge? The electron. Okay, so we have to be a little careful about this. And this is that difference that we talked about between diamagnetism, paramagnetism, and ferromagnetism. We'll get into this in more detail in a few seconds. The first question we want to ask is, what is the B field over here? Because I just wrote this, right? I said that for magnetic dipoles, you have to dot it with the B field and then take the gradient in order to get the force, right? And that might be from this. I'll show the derivation in the book because I don't care the derivation. Okay. But here we assume that B is a known quantity. Gotta learn and some learns.
question.
What's B?
What
Is that obvious?
What is the magnetic?
B is B, good, and B equals? Is it obvious?
We do have two magnetic diopoles.
I guess the only validated one like that.
Well, I'm not telling you anything about what B is in shape or quantity.
Are these two the same? Like,
Yeah, we're gonna assume that the same
so I
strength.
meant, like, the left picture, where you have to turn it into the right picture, and then maybe.
Oh, no, here I was just simply talking about how we think about M.
Now we're talking about that one.
Yeah. So this is a separate problem, one that you'll do in the homework. So I believe this is 6.4 or something. Obvious here? No, I'm getting a lot of stupefied faces, right? Just like stunned into silence. And in fact, it's super not obvious. B looks like this. Okay. Mu naught over 4 pi, okay, that's almost a given. 1 over r cubed. Huh, that's weird. 3m2 dotted in the r hat direction. Okay. You would have guessed that, right? That was straightforward, yeah. Yeah. If I just gave you more time, right? Okay, so this you can find derived in the book, and that's fine. We don't have to go into this in detail. But how would you go about doing this problem? If you think about it conceptually. Is there a part that I need to draw that I haven't drawn for the close-in field? Maybe if I get rid of this. Right, so this was an external field. What does it look like if I think about a small loop of charge? This is the B field that the loop is creating. What's that? Okay, what does that mean? This is a particle. Let's imagine that it's going around and that it's a little current. Up.
Depends which way it's going.
Okay, well, let's do that, right? We should be thinking about how wires moving charges around create magnetic fields, right?
Is it moving like this or like?
So it's gonna go like this, around like this. Here's the positive charge. This is why I put it in front of the loop. That's going behind it. Okay, so it's going this way. Okay, so how are we doing this? We're taking our right hand, we're going in the direction of motion, and we're curling around the loop. So that means inside of the loop, where is the B field? Up. Good, so B is up here. Good. And then what does it do? It has to go out because it has to be smooth. And we know that on the outsides, right? If I'm doing this, it's going out and then up. So it's curling around. Right? That's not a good drawing. They don't start on top of each other. These are smooth loops, right? Okay. Is that reasonable? Okay. You will draw this out in your homework. You'll see that these pieces here, they're with this picture, right? The B field that's generated from each one of these individual electric current loops will interact with one another. Like this. Okay, and then you're just going to use this. It's fairly straightforward, but understanding how the magnetic fields in these little loops are generated is going to be important to think about where we're headed. Because I told you at the beginning that we were going to draw an analogy between magnetostatics and electrostatics. In electrostatics, we had little charges separated by some distance. And we said, okay, I understand the dipole moment there, that's not a big deal. I put it into a bunch of material, and that separation of charges, plus and negative, interact with plus and negatives nearby, such that in the middle of the material, there's no net charge. But on the edges, what happens?
Oh, like,
What's that? What would you call that? Surface charge or bound charges, right? So a dielectric can have bound charges. So we're gonna use this analogy when we begin to think about magnetic material. Because each one has a little current loop. Okay, and those currents, depending on how they're aligned in the middle, can be totally random. But if I align them all, they'll do something fun. Is that reasonable? Okay. All right, so let's talk about diamagnetism. Okay, so diamagnetism is from the orbit of the electron. Okay. F Q V cross B. And this is the electron, the E minus. So it's like that. I could draw it upside down. The M here. Let's see if the electron's going. Did I do it right? Yeah, I did it right. Okay. So in this picture, M is going this way. And that's just convention because it's a negative charge. Okay. It's like negative. If we think about depending if you have some external B field, right? And I'm not thinking about the orientation right now. But if you imagine some arbitrary orientation where B is going through, and then of course the electron is moving, it's going to feel a magnetic force, no? So in some cases, that magnetic force is going to work to slow or speed up the electron, right? Depending on the orientation. Okay. So normally we say something along the lines that the electric field or electric force is equal to the centripetal force. Right? So another way of saying that is something like 1/4 pi epsilon naught E squared over R squared. This is the orbital distance. And that's just an electron E squared over R. Right, so this is the centripetal force balanced with the electric force between the nucleus and the electron, right? And this will give us something like the velocity at every location. So if the radius gets larger, the velocity goes down. If it gets closer, the velocity goes up. This one's straightforward. You remember that one? Well, in the presence of a magnetic field, we have to add a term. Right? Okay. So we're writing something like EV bar times B. Now what this is saying is this is going to be a a second order perturbation. What I mean by that is, for the most part, this is the right V, but there's going to be a small difference here. Okay. And that change in the velocity at delta V is actually E R B over 2 mass of the electron. So these three things we don't get to change the value of. 2 we don't get to change the value of. And E we don't get to change the value of. R and B we do. Right. And you'll notice here that the velocity is increasing or decreasing proportionally to the magnetic field itself. Right. So if you're going opposite to the direction of the magnetic field, how does the velocity change in an electron? Slows down. So let's imagine that there's a magnetic field that's going from that wall to this wall, and I am orbiting in this plane. As I'm heading towards it in that direction, slow down, and as I go this way, nothing. And then this way, fast. See the change to the orbit now? This one is obvious too. The opposite. Okay. Now here's the question. You may or may not recall from last semester. Can magnetic fields do work?
No.
Ooh. That was quick and contentious. Everyone agree? Everyone agree? Raise your hand if you agree. Raise your hand if you disagree. Raise your hand if you don't remember. Okay, so you're gonna want to read that section. Rolando, why can't magnetic fields do any work?
I definitely read the section, but what what I remember is that they said that the magnetic fields don't do work, but rather like the current that you put through, like from the battery, it's put through like the wire does all the work.
Mhm.
So we can't do-
Yeah, there's a mathematical proof that we can show in the book. If you're very curious, we can do it at the beginning of next class. But I would certainly, you don't want to do it in the next class, okay? Reread that section. It's just the conservative forces argument, essentially. And magnetic forces do no work. That's the basic line. Okay, but I just said that the velocity is changing, speeding up and slowing down the particle. So who's doing the work? The electron's doing the work on itself? What?
So what was the question?
She has got it. Nothing? The E field. Where's the E field?
Isn't there usually an equal with magnetic fields?
So interestingly enough, this is not that far off. So in order to generate the B field, okay, we're going to create a time varying magnetic field. So for example, here, I just had a balance between these two things. They were existing, they didn't know anything about B. And then I turned on B. Right? This new B changes E in a way that we're not going to talk about yet, and which generates the work necessary to change the electron.
You said it again.
Yeah. You'll need it a few more times because this is how light gets made. Okay, we haven't even started to connect these two things, but you need to be thinking about this now, which is why I asked you to think about whether or not B fields do work. In fact, E fields do all of the heavy lifting. Okay, so imagine a world in which you just have an electron going around an atom, just living its best life. Okay, moving around. And then I turn on B. That's a switch in a magnetic world that I created, right? This wall is some super magnet or something. Okay, that generates changes in the E field. That dE/dt generates the work. Make sense? You'll see more examples of this when we combine the two. But conceptually, you need to know it now, right now. Okay. This is V. This is the speed at which the electron is going around. So if I think about the current just in terms of the things that I have here, how would I write current being proportional? Current is proportional. I is proportional to what?
Yeah.
VR? What? Where's the R come from?
Oh.
I like V. What does V mean? Yeah, it's like per unit time. And what is the thing in the current?
Oh,
Charge, yeah, good. So QV kind of seems right. Right? This is not a definition. But when I'm thinking about an electron, if the electron's going around faster, is that a bigger or smaller current? Bigger current, good. And if it's going around really slowly, how's the current? Small. If there's a lot of charge going around slowly? Big. Okay, yeah, we don't know, right? So these are the product of the things. So for a single electron, thinking about changes in the velocity mean that you have changes in the current, no? This is why I put this up here. It's not arbitrary. Okay. So, you might say something along the lines of M, this is the magnetic dipole moment, is the current times A. Okay. And we'll define some of these more. So one thing that's gonna, as I goes up, M goes up. And current goes up, M goes up. We have this picture. Here. So this is the external magnetic field. External V. Okay. We turn it on. Okay. You speed up this electron, slow it down, speed it up, slow it down, depending on how it's oriented. In this particular configuration, how is it oriented? Speed going up. No, I'm asking only here about how does the magnetic field in that configuration change the velocity?
Oh, change the velocity.
Okay, where's the velocity? It does or it doesn't?
Done.
Raise your hand for does. Raise your hand for doesn't. Raise your hand for I don't know. I don't have hands. I'm giving everyone the third option. Okay, V is which way? Let's imagine into the board.
Hmm,
And B is up,
yeah.
so that is V cross B.
Hmm.
Right? There's a force. It's inwards. It's faster. Yeah, because remember we just showed this here, right? The presence of a magnetic field, or here, right? Is proportional to the strength of B, right? We just showed this. So you have a magnetic field. You increase the current because you increase the velocity. But if I have a moving magnetic field, if I change the velocity, I change the current, what does a changing current produce?
Oh, magnetic.
Magnetic field. And that magnetic field will oppose the original one.
That's why it's not like exponentially speeding up, right?
Well, there's just a small, you just get a small change, right? It like tries to balance itself out.
Is that Lenz's one?
Yes, yes. But now we're thinking about it from the context of an individual atom, as opposed to just stating this rate of change. Okay. So M is gonna oppose B.
I was forced into the board. But you said it's the force is into the board.
V, no, the velocity is into the board.
Oh,
V cross with B, right? Because aren't you like this? V cross B,
oh,
and then the force is outwards or inwards, depending on whether or not.
oh, okay.
What? Well, you have to, either one is fine, right? So V cross B. No matter which one you use. Yeah.
Is that A vector just the magnetic potential?
No, that would be capital A. I forgot what I had written down here. Let's just write this as proportional right now. I'll define that better later.
Okay.
If you start with M parallel to B, you still slow this down from the orbit of the electron, and M still opposes B. Do we see that?
Would it be external? Or do we-
Yeah, this be external, right? As opposed to anti-parallel, if you flip it over.
Okay.
Because now let's do it again. Okay, you're still doing the velocity. B is now down. So what's that?
Outward.
So V cross B, and it's going outwards. B cross B is going inwards from this point, and then as I go around, always inwards. I guess B is still down.
Okay, I see this.
He's either up or down. Okay. So typically when you think about a material, all the atoms, dipoles in there, randomly oriented. Right? So that's why this wood is not magnetic. If you put things into a B field, some stuff will slightly oppose the B, right? That's diamagnetism. It's weaker than paramagnetism. That's usually only thing, diamagnetism is seen with things with even numbers of P minus. And this whole description that I'm giving you, of course, is flawed. And why is it flawed? Yeah, this whole description. Two particles are really quantum mechanical in nature. So we are treating them like they are rods or wires. That's not true. They're probability clouds going around one another. You have a likelihood to find them in a certain location at a certain velocity. So all of this discussion about differences in the velocity, it's like an expectation of differences in the velocity. So at some point, you may be forced to reckon with this. You have quantum mechanics that you're taking right now. You have E&M that you're taking right now. We're treating in E&M these individual particles as point particles with definite velocities. And the reality is that's not the case. But it'll work or not. Okay. Okay. All right. But you'll need to come back to this when we think about quantum field theory. Okay. Does anyone know what ferromagnetism is? Okay. Ferromagnetism is what?
Material that keeps polarization and leads in the electric field.
Yeah, exactly right. Oh, that's not right. There's no Z. Good. And these are things like iron, nickel, cobalt. Good. This one has an unpaired electron spin, but now it wants to match its neighbors. Okay, and I'm not going to explain why this is, because it doesn't make any sense because of quantum mechanics. Okay, so quantum mechanics says that an unpaired, that is to say, he doesn't have a friend inside of his little shell, wants to match neighbors. Okay, and this leads to one of the most fun curves in E&M. I know what it is before I read it. Now this will be external magnetic field. Hysteresis curve, very good. And then this is the magnetization. Okay. So let's write, let's imagine that we have some item, this chunk of iron. Do you want to try? You have a chunk of iron and it's initially unmagnetized. So to start here. Okay. And then I apply a magnetic field in this direction. Okay. So let's imagine this is so this is your magnetic or your iron object or nickel object, and I'm going to apply a B field that direction. Okay. At first, I'm sorry, I marked it. At first, you can have a sticker. At first, every dipole moment in there is random, completely random, whatever orientation it is. And then slowly, right, as you apply more and more B field, right? Okay, it's slow at first, and then it happens all at once. Right? And you get to some peak magnetization of the material itself. Now, it's not able to fully align everything all at once and give you huge magnetic fields because objects have inherent abilities to magnetize. Right? Those would be like 1.9 or whatever the magnetic susceptibility of the object is. Okay, good. So even though you try to apply more to it, you can't, you get a maximum magnetization. Everything's pointing in one direction. And now you turn it around. So instead of applying the magnetic field in this direction, I apply it backwards. Now what happens? Does it go back down this path?
Yeah.
Can it ever go back to 0? Raise your hand for yes, it can go back to 0. All right, ask your friend for a second. Let's take 5 minutes. Ask your friend whether it can go back to 0. Draw on your paper what the curve looks like. As you go from this direction.
I think things could be under.
And then this one.
Opposite magnetic.
just.
You just post it.
So-
It do post
I mean, you can go back to zero and just like, you do the tricky thing. and just do it back.
And then it is longer, like you said.
But I, like, for the-
With 0, you mean like the origin?
Yes.
0, oh, no. Oh.
I was thinking maybe this way.
Yeah. I just thought back. I can just, I should.
Okay, well, you haven't read it.
Huh?
That's not right.
Well, what are your thoughts?
That isn't right. My access is wrong.
I don't know, what do you think?
Don't just think about what you've already seen before, think about how it would work here, understanding the principles we talked about. The fact that stuff doesn't want to align and then it does want to.
Now, where do we
Right.
think like this graph?
First, it's random, starts down here. Doesn't want to align
So this
until
is like
all of its
no-
friends are doing it, and then all of its friends do it, so it
Like
does it.
completely random.
Now apply that the whole time. Back and forth and show me the whole curve.
So, no.
None of them. Plus they're gonna stay back since this point. For one, that's so. Or is it right away and then?
What happens when I return it right next year?
What?
Okay, so I applied a magnetic field, and I applied it going this direction, and then I turned it around, I put it in that direction. So it goes back to here, and then it just stops.
Direction.
It's gonna, it's polarization. Well, it's gonna stay at its highest level until you start going the opposite external field.
Okay, so you want it to be this?
No, that doesn't make any sense. I was gonna continue it on the bottom.
And then when it starts getting to the negative field, it starts going, it starts going down.
But they have.
the same way.
Like this?
Yes.
I mean, it's already.
Yeah.
Yeah.
Zero?
No, I'm free. I feel like I'm fighting.
What?
I don't know, that's my-
Yes, yeah, and then back down, back.
I'm sure it's.
Out of the field. I go back to 0, it doesn't care.
Yeah.
If I go to student help, can you spin all this again?
That's a problem that you're gonna do.
Oh, yeah.
Yeah, that's the first one problem. Get to the top, it says explain more. Yeah.
Oh, yeah.
You saw this in the booklet, right? You read the book.
Yeah, I'm not sure if.
That'll help. Try it.
Like, external piece.
Oh,
Like,
okay.
and
Let me double check that it's 6.4 though.
then-
Go ahead.
What did it say on the bottom? Almost the same.
So like, what do
Okay,
you?
alright. Let's see if that's right.
I think it's 6.3.
I don't know.
Think I can, at least try.
6.3, sorry. Alright. Okay, so we said at the very beginning that all of the magnetic dipole orientations are random. And we said that the E unpaired wants to match with its neighbors. So if I can convince some of its friends to match, right, then all of them will join, because they don't want to be the last one, right? So once everyone starts wearing white Air Force Ones, then they all wear white Air Force Ones, right? Okay, so at first, nobody is wearing them. Right? Oh, sorry. So at first, no one's wearing them, right? But then it gets really trendy. And then everyone's like, oh, that looks really cool. And then they all start wearing them. Okay, so now what happens when the trend starts to move away from that type of fashion and maybe more towards like high, what are they called? The high chucks. Yeah. What happens? Which one? This one? This one? Something different? Gonna show us this one? Is this flat line correct? No. Because as soon as you stop putting this external pressure on these electrons, some of them switch back. So you already will start to see some downward from this. Okay? And then here, You still have a lot of people wearing them. Right? But now there's a big push to wear Chucks. So now what happens?
That's the other direction.
Okay, polarizing the other direction. So let's imagine that, why does this one so bad? This was just good 2 seconds ago, right? Alright, that's better. Okay, so now where are we going? Up like this?
You're gonna be magnetized, but like it's
So you're gonna do the opposite.
magnetized.
Let's remove some of these extra lines. So these ones up here are not wrong. I'm sorry, are not right. Sorry. So now we think that it goes like this.
No. Oh,
It's gonna go in the opposite field, so we're going like this. What?
Not loud.
I don't know, you tell me.
I think.
What does magnetization mean here?
If that's why Air Forces is up for magnetism, then down would be the chucks.
Right.
And you would be the high.
Right, because remember what these mean. These are external magnetic field directions. So this is large and positive versus large and negative. Okay, this one here would be large and positive and large and negative. So these have to be aligned, right? This one is matched with this one and this one is matched with this one. So whatever arbitrary thing they are, right? Like speeding, right, when you're a kid versus like hanging out behind the high school. I don't know. I'm trying to relate to the kids. How do I get through to them? You know, there's like fads that people do. I don't know if you were you guys alive for planking?
yes.
Okay, good.
Exactly.
Planking is up here versus what's another trend? Swatting. Okay. Swatting. Does this make sense?
Oh, you don't know swatting?
No, we're not talking about it here. Okay, so the point is here that these will be aligned, right? That this push, this external push for this trend is gonna result in this over here. But the way that we connect them is, well, smoother than that, that's for sure. Okay. Is that right? Let's think about what's happening in here. First, we apply this external pressure. At first, many of the unaligned electrons do not want to align. So it takes a while. And then it slowly builds up and it quickly comes to saturation. Okay, on the way back, they don't want to unalign. Now they're getting peeled off one by one. Let's assume that that's like halfway. Okay. Oh God, this is like the worst thing that ever existed. Okay, let's assume that this is some sizable difference, right? As you go down. Okay. Now you still have many of them in this external trend, even though the source of the trend is gone. So if you stopped here, you would remain with what type of object? Magnetic object, right? Not as strong as when it was in the strong magnetic field, but it's still there. Okay, now you reverse it. And you have to turn it around so that it goes through zero out here in the presence of an oppositely aligned magnetic field, bringing it down from here to here. So now you've removed all the magnetization. Now it's random again. And now you need to convince it to go the other way. So you have to apply more magnetic field. You see? And then it's the same thing back and forth. Can you ever get it back to here? No. Okay, this is a hysteresis curve. This is a time curve, right? Which is reversible in this section, but you can never get it back to its origin. Okay. All right. So we put stuff into a magnetic field and the little dipoles line up. Right? Unlike the polarization vector for electric fields, this can go either way. Okay, we can orient these dipoles however we want, as we just showed you. Okay, and this process is called magnetization. This is something you already know the word of. Did you find the Insane Clown Posse song?
No.
You,
We texted you,
And I
and
never
you like
answered.
never answered, because you didn't.
Oh, maybe I didn't click send on that message. It's called Magic is Everywhere. I swear that I wrote that out. Maybe that'll be the welcome music for next Thursday's. It's bad, it's not good. Alright. We good? Okay, so we call this magnetization. Okay, very uniquely, this is defined with a big M. You'd think that I would know how to spell it? No. Okay, so this is I know that's because I read it.
Oh.
I just almost put an S. Okay, so here we have the magnetic dipole moment. Per unit volume. What does that look like? Where have I written something similar to that? Polarization.
You can say it.
Yeah, you gotta say it loud. Polarization, right? Electric dipole moment over the volume. So that was the big P, right? As opposed to the little p. So we took all the little p's, we made it a big P. Now we're taking all the little m's, we're making a big M. Okay? Okay. So how do we get this? We're gonna get the magnetization, the total magnetization. They're vectors. Add them. That's close, yeah, sum. And we like for continuous objects, integrals. Ah, she had her opportunity for an integral and she chose sigma. Unbelievable. All right. Is that reasonable? So we divided, let's remember, right? P into rho B and sigma B. I know you deleted this already, right? Okay, what was P, what was rho B, what was sigma B?
Bound volume charge and bound surface charge.
Bound volume charge and bound surface charge from this polarization vector, the total polarization for the material. Okay. So essentially we said something along the lines of we have some material and there's individual items in here, electrons, right? Minus, 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 minus. Oh, that's not gonna come out then. Well, pluses, let's do pluses and minuses, right? Little pluses and minuses everywhere, okay? And that was like this like real idea that we had inside. And then we sent it somewhere to think about, well, really that's like a bunch of little random polarization arrows, right? This, that, right? That was the second way of thinking about it. And then we summed them all up and we said, well, that really kind of looks like, you know, like this. Right? And then everything else cancels. That's these levels of abstraction for the E field. Do we see that or not? Okay. So now let's think about it in the context of loops. So in a material, you have little atoms, right? Individual atoms. Okay, electron, okay, positive like that. Yeah. Maybe over here, that, over here backwards, like that. For individual loops. Okay, and this would lead to our understanding of some magnetic dipole moment. M, 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 right? But each one of those is representing a loop. Okay. If I write them just, let's imagine that it's a 2D object, there's no third orientation that's possible, okay? There's going to be, let's say in a perfectly magnetized material, all the loops are oriented in the same way. I'm gonna draw a very bad picture, but you're gonna like it, okay? So here's the loop 1, here's the loop 2, 3, 4. Okay. So in this section right here, the current. Yeah, what's the current in that section, right? Because these are all current loops, no?
Yeah.
Yeah,
How does it work?
here,
I like that.
take these two loops, one that goes up and one that goes down.
Oh.
One that's going up like that and one that's going down like that. In this little box here,
Oh.
0, right? So in this picture over here, we had these differences in charges that are inside the material canceling out. Right? And in some cases here, you'll have loops that are aligned so that inside the material, the current cancels out. But on the outside here, I have plus, 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 plus. I have current that appears to be moving on the surface. See that? Okay. So we are going to get volume and surface currents, Jm and Km. This is a volume. That analogy make sense? All right. That a bunch of times. Let's derive this. To the vector potential. The vector potential for a single object. This. Oh, whoops, not integrated, that's fine. And for all of them. Okay. So what am I saying here? So for a single object, we can write the magnetic vector potential like this. And just like we have this collection of individual magnetic dipoles, here we're going to integrate them. Just like we integrated the total magnetization vector, we get the magnetization of the object. Here, we're going to derive the magnetic potential, which would eventually give us the magnetic field for any object. Because the magnetization is due only to the loops inside. It's great Tuesday morning math. Okay, so let's use okay. Haters. This one okay?
Yeah.
Is this one okay?
Yeah.
I'm not gonna write these all out. This is an identity that you should probably pay attention to. I think this one will be in your book. This is hidden somewhere in your book. I think it's hidden in I don't remember what problem. Okay. So you want to use, you're trying to use Stokes here. But you have a volumes that you have to take into consideration as opposed to just the surface integral for this cross product. So we can't just jump through this one. So instead, we're going to say that A is equal to not find the volume integral of 1 over R. And that's this piece here. Del cross M. See this one here? Okay, easy. Or d tau, whatever you want to call it. Plus mu naught 4 pi, the surface integral of 1 over R M cross dA. Okay. This conversion right here is one that's hidden in your book. But we're breaking this apart into 2 pieces. Okay, and what I'm trying to say here is what I've been sort of hammering, but now we're going to show in math. Okay, this is the magnetic potential. This is what gives rise to the magnetic fields that we see in everyday life. And it comes from 2 terms. These 2 terms look like absolute garbage, right? No intuition at all, right? But we'll see them in 2 seconds here. Okay. This del cross M, okay, this is our definition of J, our volume current. Okay. And this one here, we can write this as, we can write it like this too. This is perfectly fine. This one here is how I want to define K M. And Km is okay. Surface current. Okay. So what does this say? Okay, this becomes, I mean, relatively easy, relatively straightforward, I should say, not easy. This becomes straightforward to understand that the A, maybe I'll just tighten it up here. Mu naught or 4 pi, that's on both, is the integral, the volume integral of Jm over R d tau plus the surface integral of K M over R dA. Okay. So this is what I claimed. Right? That makes sense? So if we can find bound currents, if you can find volume currents, then you have the magnetic field. Okay, so defining these things is the only hard part. Integrals are straightforward, right?
You're saying A is magnetism?
No. A is what? A is not B.
Is it over a closed surface as well?
Probably. How is B related to A? What is A? What is big A,
Magnetic potential.
right? And specifically the magnetic, what kind of potential? Vector potential, that's right.
Okay.
Okay, so how do I write this? Del cross that. Right? I mean, you know this for V. So in magnetism, okay. You have this. And for electric, you have E not equal to V. What?
Is that a negative gradient?
Okay, so how do I write that?
E is equal to negative gradient
Okay, and this is what?
scalar.
It's a scalar. It's a scalar potential. Right? We started off on Tuesday, I believe, talking about how there are non-unique solutions for A to get B. Okay. So if we have a way to calculate A not from B, but from A itself, then that's better. Right? Okay. It's not going anywhere. So when we talk about the magnetization of materials, we are applying a B field, right? Some stuff becomes magnetized. That magnetization is a function of B, and it's either parallel or anti-parallel, depending on the material itself, depending on the electrons. So we can write the magnetization, just to really fuck with everyone here. And we can write it as a function of something called H. Okay. We develop M as a function of H. Why? Because you historically, you control H with free currents, and H was considered more important. Okay, so let's consider a line current with no matter. Line current, no matter. Ampere's law says. You remember that one? No, that's okay.
Oh, I have.
You found it? Good, I can read that super good. What did it say? Let's use an analogy to B here. We're going to call this H. What was that?
Oh. You not F or something?
Okay, okay. You're going to see some analogies here. So let's call it I, F enclosed. Okay. I'm thinking only about a magnetic field with no matter. I have something like this. Let's assume that I did that del right. Okay, so this is probably what you have in your book, no? Or in your notes. The second one.
Yeah.
Okay. This one, that looks similar. Free. And so then H is just I over 2 pi s in the radial hat direction. Or sorry, in the phi direction. Okay. Whereas this one here, B was mu naught I for 2 pi s. Huh. Those are really different, huh? What's that? Is this a mu naught? What'd you say? That's crazy. Oh, I thought you said displacement. Because you should be noticing an analogy. Remember we talked at ends such a long time about the fact that D and E were related, right? And that they only basically differed by a factor of epsilon of some variety, and you can look that up in your book. So here I created this thing called H, which is a function of the free currents in the system, right? Because as I apply a magnetic field to a material that has the ability to generate its own little baby magnetic fields, it will oppose those magnetic fields, right? Reducing the magnetic field strength overall. So therefore, we write something like this: B is equal to mu naught H minus M. Where have I seen this statement before?
In displacement,
What's that?
with displacement.
With displacement, right? So in the past, we had something like E was
Times D
D
minus forward.
minus. Okay. Oh, that's a funny little analogy, isn't that? That's really random. Who would have thought they would be constructed so much the same? Okay, so here what this bottom one is saying is that the displacement field, right, is reduced by the presence of polarization. Right? Or sorry, the electric field is reduced by the presence of polarization. Here, this is saying that the H field is reduced by magnetization, right? So if there is no magnetic dipoles in the material, then these are the same. If the material is not polarizable, then these are the same. Right? No one has any questions about that? I feel totally comfortable with it, right?
I can use another explanation
Okay.
for,
That's good.
for the, how E and B are kind of analogous to each other. Because what you, so big confused on like the overall concept of displacement.
Okay. So let's do displacement again. Okay, here is a capacitor. Okay. The E field in this section goes from positive to negative. Okay. So this is E. And then let's assume that in this section, I have a material. Dielectric. Okay, that dielectric can be polarized. So it does. And what does it do? How does it collect charges? Negatives at the bottom? Positives at the bottom. Good. Positives at the bottom, because they're attracted to the negatives, and here, negatives at the top. Okay, and this is D. Okay. How are these related? Let's put P in here too. Where's P? Like that, right? Here, P is 0. So that's the analogy that we use to understand this bottom one. Here I have a material, okay, that will act in the same way. And let's have some object like this. Okay. Let's run a B field through it. E just going through nothing. Let's imagine there's nothing on this side. Because that'll be our normal analogy. B. Here, however, let's have a material that is able to be magnetically polarized. Okay, you get little current loops. Okay. And each one of these little current loops wants to oppose the incoming magnetic field. Okay. So the magnetic polarization and the electric polarization act to do the same thing. Materials don't like when stuff runs, well, they don't actually have a feeling about this, but they seem to appear to oppose these types of motion, right? When we talk about magnetic fields in detail, when we think about particles moving in time-varying magnetic fields like to act like rubber bands. So you've seen that how a metal detector works. You saw that in the 2500 series, right? Lenz's law. You walk through a magnetic field, and then your presence of a piece of metal generates back currents that sets off the alarm. You've never heard of this? No. All right. Okay, so this is how metal detectors. Large enough piece of metal heading through. Right, oh shit, I deleted all the ferromagnetic stuff. Okay, it doesn't want to be oriented. It generates fields to oppose that. And that's what the detector picks up.
What does it mean when like it gets something and you don't have anything? And they'll say like, oh, what's that? Right, and they start searching.
That's just faulty equipment. Yeah. Or maybe like a large concentration of gold in your pocket, you know? No, but you don't have enough metals in your body to do that.
Okay.
And the water inside your body is not orientable in the same way. Right? Your water, the water that makes up the majority of your cells, does not have ferromagnetic properties. Right? It's diamagnetic at best. Okay. Does this analogy make a little bit of sense? Yeah.
So would H be on the right side then?
Yes, sorry. Because let's imagine some, and I'm probably gonna get these orientations wrong. Yeah, I think I'm getting the orientations right. But if I'm not, I apologize. It's not written in my notes. I'm just freeballing these, okay? So,
I was gonna say, does this only work with ferromagnetic materials, or is this the same for diamagnetic, like this formula? Right?
no, so this formalism that we're talking about is uniform. And it comes from the fact that I can generate here magnetic fields from volume and surface charges. So this is just a picture, right? This is a mental model that I'm constructing, but the real result is the same. Now, in practice, in this material, you have these current loops, most of them are doing whatever they want. They're not doing that much. But even if I have a small amount of alignment, whether this is due to ferromagnetism, whether this is due to diamagnetism, whether this is due to paramagnetism, I don't care. I don't care what the material is. I care that you have a surface charge. Surface current, right? That surface current or that volume current is something that's measurable. So the presence of these two things that I can see, right, lead to something that I can predict, like a magnetic field. The actual interior parts, you know, someone who cares about solid state, someone who cares about condensed matter, they would be great. They'd tell you so much about this. Oh, the structure of the electron, I don't. Okay. All I care is that we are looking fundamentally here how materials interacting with matter choose to generate their own either magnetic fields or electric fields that appear to oppose the original. Okay. And this analogy here is not just mathematical. The reason that we're taking a class called E&M is because we're going to connect these phenomena. E doesn't happen without M, and M doesn't happen without M. Okay. Questions? Okay. So I deleted it, but 6.3 is the first one for this homework. If you didn't have enough time, start back. Write more. 1 page, not enough. More words, more better. More algebra, more better. What?
Only algebra bad.
What? Only algebra bad, yes, very good, very good point. Anyone else still owe me a homework?
Yeah.
Can I just put the homework in your cubby?
Yeah, we start leaving fast on the ground.
Oh, I'm gonna have that. I'm gonna find out who's in here afterwards. Right to you.
Straight through jail.
Believe it or not.
Yeah.
Dr. Krismani. Hello. Sorry.